Hello everyone. Today let's study the last class of this semester, the hearing and balance. Where the hearing and balance is so the major organ that work for the hearing and the balance is the ear. Okay, it's the ear. So actually, so the ear it consists of three parts. Okay, so as we can see in this slide, these three parts are actual. So these three parts are the first is the external ear, so the second is the middle ear, so the third is the inner ear. Okay, so let me open this small pane. So this external ear, middle ear, and internal ear. Okay. We can see the external ear is from the auricle, okay, from the auricle to the end of the ear canal, okay, ear canal. So the ear canal is called external acoustic meters, okay, in the end of the external acoustic meters. So in the end of the external acoustic meters, so we can see there is the membrane. This membrane is called a tympanic membrane, okay. So the middle ear, actually is from the tympanic membrane and to the stapes, okay, to the stapes, this part, okay. Actually, so the middle ear is bony cavity, okay, it's the bony cavity. This cavity actually is linked to the external environment through the pharyngeal tympanic tube. Okay, so the pharyngeal tympanic tube actually can let the ear can let the ear can let the ear get in or get out from the middle ear to maintain the equal air pressure in the middle ear as external environment. Okay. So the internal ear actually is from the from the overall window. Okay, from the overall actually from the stapes. Okay, and to the ocular nerve. Okay, so now let me see the external ear. External ear, so we can see external ear has the auricle. Okay, auricle actually is the elastic connective tissue. Okay, and then so the body of the auricle is called a helix. Okay, in the bottom of the auricle we can so we have a tissue. Okay, this tissue is filled with a fat tissue is called a lobule. Okay, and the auricle function is to collect all the air sound. Okay, and guide the air sound to the external acoustic meters. So the external acoustic meters function is to conduct the air sound from the auricle to the middle ear. The middle ear, we can see the middle ear is the middle of the membrane, so tympanic membrane and three small bones. Okay, actually, so the middle ear's function is to amplify the air sound, and so its function is also to convert the air vibration to the mechanical vibration. Okay, because the air sound is actually the air vibration, right? Where the inner ear's function is to convert the mechanical vibration to the nervous action potential, and then transfer the nervous action potential to the brain to let the brain generate the hearing. Okay, so this is the ear. Now let's zoom in the middle and internal ear. Okay, so we can see. So this is the middle ear. Okay, middle ear. So this is the tympanic membrane. So the tympanic membrane is a very thin membrane. Okay, so it is very sensitive to the air vibration. So it can convert the air vibration to the mechanical vibration. And then, so we have three tiny bones. Okay, these three tiny bones actually transfer the mechanical vibration to the to the vestibule. Okay, to the vestibule. So these three tiny bones are the malleus, okay, incus, stapes, okay. So these three bones are called auditory ossicles. So the malleus is like a hammer, okay. Incus is also called anvil. Stapes is called stirrup, okay. So we can see so these are the three tiny bones. So here we have the mastoid antrum. Mastoid antrum is bony space in the temporal bones. Okay. So this small cavity actually, so its function is to buffer the ear, buffer the air of the middle ear. Okay, for example, if the so if the air in the if the air in the middle ear is becomes less, so the mastoid antrum can because since the mastoid antrum is the cavity, so there are some air in this cavity, so this air can flow out to the middle ear to compensate the decreasing air pressure. Okay. Now, so here is the inner ear. Here is inner ear. We can see. So this part is called a vestibule. Okay, vestibule. So in this, so the vestibule have three canals. Okay, so we call these three canals as the semicircular canals. Okay, and then so below the vestibule, so we have a snare share like a structure. So this is all called a cochlear. Okay, cochlear. Cochlear has the nerve attached. So this nerve is called the cochlear nerve. Okay, vestibule also is attached by the nerve. So this is called the vestibular nerve. Okay, here we can see the middle ear. So the middle ear is attached by the pharyngeal tympanic tube. Okay, so because this is tube is to compensate the air pressure in the middle ear. So so the vestibule. So the vestibule on the wall of the vestibule, so we have two windows. So here is the oval window. Okay, or oval window. And we have a round window. So the oval window is very important because the stapes, directly tap on the oval window. Okay, so once this auditory ossicles transfers the mechanical vibration to the vestibule. So the stapes directly hit on the oval window to transfer the mechanical vibration to the vestibule and to the cochlea to generate the hearing. Okay. So now let's zoom in the auditory ossicles. Okay, auditory ossicles. So we can see. So here is the malleus. Okay, malleus is also is known as the hammer. It's the first obstacles. Okay, we can see the malleus is attached by a tiny muscle. So tiny muscle is called a tensor tympanic muscle. Okay, tensor tympanic muscle is very important because this muscle's function is to regulate the noise. Okay, to regulate noise. For example, so when we um, when we eat our lunch, okay, when we eat our lunch, so when we chew, okay, when we chew, so the chew will generate a huge noise, okay, and so if, for example, when we are eating, okay, so this is small, tiny, so this tiny muscle, tensor tympanic muscle, is contract, okay. So this tiny muscle contract and pulls the malleus and pulls the tympanic membrane to make the tympanic membrane very tight. Okay, very tight. So if the tympanic membrane is tight, so it's difficult for this membrane to vibrate. Okay, so that means it can dump the vibration. Okay, dump the vibration to decrease the mechanical vibration induced by the air vibration. Okay, so if the so that means if the tympanic membrane is tight, so it will decrease the vibration. So if the vibration decreases, that means the hair. So the hearing, so we don't hear too much of the noise. Okay. So that's the function of the tensor tympani muscle. Okay. And here we can see, so the second is incus, so the third is stapes. Actually, we can see stapes is also attached by a tiny muscle. It's called stapedius muscle. Okay, stapedius muscle. So very interesting. So the stapedius muscle is the smallest skeletal muscle in our body. Okay, so this smallest skeletal muscle's function is to stabilize the stapes. Okay, stabilize the stapes. Since stapes is a tiny muscle that hit the oval window to generate the hearing, so the stapedius muscle can stabilize these tiny bones and to let this tiny bone uh, to perform very well. Okay. So here is the epitympanic recess. Epitympanic recess. So its function is also this function is to amplify the vibration. Okay. And then here we know, so this is pharyngeal tympanic tube. Okay. So this is ear obstacles. Now let's move to the inner ear. Okay, inner ear. So here we can see this is stapes. Stapes is directly attached to the oval window. Okay, so here actually stapes is attached to the vestibule. Okay, vestibule. Vestibule has two very important structure. The first is the auricle. Okay, auricle is on the top. So in the bottom is the second important structure is called sacral. Okay, sacral. We can see the sacral actually link with with so the sacral is linked with the ocular. Okay, ocular. So the ocular is the snare shear like structure. Okay, so the we can see it's like a spiral tube. Okay, so the tube is called the cochlear tube. Okay, cochlear tube. So the cochlear tube. So between the two, you can see we have this bony structure is called a spiral organ of Corti. Okay. So in the auricle and sacral, so all these structures have the important structure. This is called maculae. Okay, maculae. We'll talk about this later. So the oculum actually is the organ to generate the hearing. Okay, so the hearing nervous action potential will be transferred to the brain through the ocular nerve. Okay, ocular nerve. Now, so on top of the vestibule, so we have the three canals. Okay, so these three canals are called semicircular ducts. Okay, semicircular ducts. Okay, so the since we have three semicircular ducts. Okay, so these are the anterior, posterior, and the lateral semicircular duct. Okay. So this duct's function is to maintain is to generate the orientation information from our body. Okay, so the vestibular function is to maintain the balance. Okay. So now let's first look at the cochlear. Okay, cochlear. So the cochlear actually is the snare-like structure. Okay, so if we cut in half, we can see. So this is the bony structure. Okay, bony structure. Actually, since it's the snare-like structure, so it has spiral ducts. Okay, spiral ducts. So this each spiral duct we can see. So this part is called osseous spiral lamina. Okay, and so this is called cochlear duct. Okay, cochlear duct is also called scalae media. Scalae media. Okay, scalae media. So scalae media is surrounded by two ducts. Okay, so the top is called the scalae vestibule. Scalae vestibule. Okay, so the on the bottom is called scalae tympani. Okay, scalae tympani. So this is the scalae media. Okay, scalae media. Okay, scalae media. So in the bottom of scalae media, so we have a layer of cells. This is called the stria vascularis. Okay, stria vascularis. Where so we can see here is the membrane. Okay, here is the membrane between the scalae media and the scalae tympani. Okay, so this membrane is called basilar membrane. Okay, basilar membrane is very important. Okay, so we'll talk about it later. So on the top of the basilar membrane, so we have very unique structure. So this is called the spiral organ of Corti. Okay. Spiral organ of the Corti is the major tissue that generates the hearing. Okay, generate the hearing action potential. So the spiral organ of Corti actually have the so the spiral organ of Corti is innervated by the nervous fiber. Okay, so the nervous fiber will travel out of the occur. So and link together. So this is and reach to a neuron. So this is called a spiral ganglion. Okay, spiral ganglion. Spiral ganglion, and then send the axon to form the ocular nerve. Okay. So. So now let's so this is so now let's take a look at this part. Okay, take a look at this part. So we can see, so this is scalene tympani, this is scalene vestibule. Okay, so we also have a membrane here between the scalene vestibule and the scalene media. So this is called vestibular membrane. Okay, vestibular membrane. So if we took a look at vestibular membrane is also important because so this membrane actually transfers the vibration from the fluid in this cavity to the fluid in the scalene media. Okay, and then so the actually so the fluid in the scalene media is called endolymph. Okay, it's called endolymph. Endolymph. However, the fluid in the scalene, vestibule, and tympani is perilymph. Okay, the perilymph is the perilymph. So very interesting. Very interestingly, so the perilymph is highly concentrated with with the sodium and the low potassium. However, the endolymph is highly concentrated with potassium and low sodium. Okay, so this is very interesting. So now, so let's zoom in the spare organ of Corti. Okay, spare organ. So we can see this membrane. Okay, this membrane is called tectorial membrane. Okay, tectorial membrane actually attached with the hair of the hair stairs. Okay, so this is here. Okay, so the hair is directly attached to the tectorial membrane. Okay, so here is the hair stairs, outer hair stairs. Okay, and here's the hair stairs is innervated by the by the by the spiral ganglion. Okay, spiral ganglion of the ocular nerve. Okay, so so the hair stairs so the hair stairs are distributed in different location. Okay, so so we have the outer hair layer. Outer hair layers means this hair layers are located in the peripheral side. Okay, however, in the central side is called inner hair layer. Okay, this is inner hair layer. So all the hair layers are linked with the nerve fibers. Okay. So the hair cells attached with the supporting cells. Okay, supporting cells is to support the hair cells to stabilize the hair cells. And then, so on the bottom is the basilar membrane. Okay, basilar membrane. So here, let's talk about the stria vascularis. What is the function of the stria vascularis? So here, as what we know, so the endolymph is highly concentrated with the potassium. Okay, so why is the endolymph highly concentrated with potassium? That's because the stria vascularis has certain potassium sodium bumps. So these bumps actually continuously bump the potassium into the endolymph. So that's why the endolymph is highly concentrated with the potassium. Okay, because we cannot see the stria vascularis in either scala vestibuli or the scala tympani. So that's why so the scala media is highly concentrated with potassium. So now this is the scanning electronic microscope view of the hair cells. So the hair cells is the basic cellular unit that generates hearing action potential. Okay. So now, so if we cut the so this is octa. Okay. So if we cut the octa, so this is cut in half. Okay. So if we cut in the other way. Okay. So we can see. So if we cut sagittally, so we can see. So this is the basilar membrane. Okay, this is the basilar membrane, and so this is ocular duct, and this is the perilymph. Okay, perilymph. Actually, so the basilar membrane. So basilar membrane, since basilar membrane has hair cells. Okay, so the hair cells actually, so the hair in the different location of the basilar membrane, so the hair length is different. Hair length is different. Okay, so in the region of the oval window. Okay, so in this part, so the hair length is very less. Okay, however, in the terminal part, so the hair length is long. Okay, so that's why. So in the base part, so the hair cells is very sensitive to the high frequency mechanical vibration. Okay, however, in the terminal region, so the hair cells are very sensitive to the low frequency vibration. So the region is between 20 and 20,000 hertz. Okay, so that means so our ear can hear the sound. So the sound vibration between 20 and 20,000 hertz. Okay, so actually, the human speech. So the human speech is between 1,500 to 4,000 hertz. Okay. So obviously, so the human speech is in the region of the ear hearing. Okay. So this is the resonance sense. Resonance sense of the basilar membrane. Okay. Now let's talk about the sound. Okay. So the sound actually, air sound is just the air vibration. Okay. And so this is physical knowledge. Okay. So we can describe the characteristics of the sound as amplitude and the frequency. Okay, so the first is the amplitude. Okay, so the amplitude actually is so we use the so we can measure the amplitude with decibel. Okay, decibel dB. Okay, so the amplitude represents the energy of the sound. Okay, for example, if we speak loud, okay, that means the amplitude is very high. Okay, so this is the term to describe the loudness. Okay, loudness. So that's for the sounds intensity. Okay, So if the amplitude is high, so the decibel is, and so decibel is high. Okay, that means this sound has a high energy. Okay, so if we look at this graph, okay, so so this is the sound wave. Okay, so we can see. So if we measure from the wave peak and wave bottom, so if we measure from crest to throne, okay, so the distance from crest to the throne actually is the amplitude. So amplitude actually represents the energy, so loudness of the air sound. Okay. However, this distance represents the frequency of the sound. Okay. So the frequency of the sound actually represents the characteristics of the sound. Okay, for example, so the woman's speech is different from the man's speech because so the woman speech has a higher frequency than the man's speech. Okay, so the transmission of the sound to the inner ear. Okay, so the root is that. So first of all, once the air sound reach to the outer ear, okay, so reach to the pinna auditory canal, okay, and then travel to the middle ear, okay, middle ear to hit on the tympanic membrane, okay, tympanic membrane and transfers the air vibration to the mechanical vibration, and then so this mechanical vibration will be transferred to the inner ear through the auditory osseous. So the auditory ossicle, like the malleus, incus, and stapes, okay, to the over window, okay. So once the stapes hit on the over windows, so this mechanical vibration will transferred to the scala vestibuli, okay, scala vestibuli, and then so the vibration will transfer to the scala media, okay, scala media to stimulate to hit the organ of the corti, okay, generate the impulse, and then so this is electronic nervous impulse action potential and then travel to the brain through the cochlear nerve, okay. So now, so let's see, since the frequency of the sound represents the characteristics of the sound, okay, so we can see here. So the blue sound actually is low frequency, okay. So the red sound is the high frequency, okay. So that means high pitch, low pitch, okay. So actually, for this one, so for this graph, okay, so the blue sound and the red sound have same amplitude, okay. So if we look at this crest, this is circle, so they are same. So this means the amplitude is same, the energy is same, okay. However, the sound characteristics is not same. Now let's look at the B. Okay, look at B. So the frequency is same. Okay, so if we measure frequency is same, however, we can see the amplitude is different. So here we can see the green sound has lower amplitude than the blue sound. That means so that means the green sound has a lower energy than the blue sound. Okay, so if we hear this sound, so we will hear the green sound is weaker than the blue sound. Okay, so if we hear the sound from figure A, okay, so actually, so these two sounds are here the same, okay, are here the same, so are here at the same amplitude, okay, amplitude. Now let's talk about the basilar, okay, basilar membrane, okay. Since we have mentioned that, so we can only, so the basilar membrane can only detect the hear sound between the 20 and 20,000 hertz, okay, 20,000 hertz. So that means outside of this region, all the air sound outside of this region, so we cannot hear, okay, so this is called, so here is audible, here is audible sound, okay. So outside of the region is called inaudible sound, okay. Yeah, so if the air sound frequency is too low, too high, so we cannot hear, okay. Because the air sound outside of the region cannot stimulate the hair cells in the basilar membrane, okay. So the audible sound actually can vibrate the basilar membrane, can excite the hair sound and generate the action potential, okay. So yeah, actually, so if we take a look at this slides, so this is how we hear the sound, okay. So we can see when we hear the sound, actually, we just transfer the air vibration energy to the nervous action potential, okay. So we just transfer the mechanical energy to the so the electronic energy, okay. However, so our ear doesn't change the frequency, okay, doesn't change the frequency. So that means so our ear doesn't change the air sound characteristics, okay. So our ear just convert the mechanical energy to the electronic energy, okay. Here we can see, so this is external ear, okay. So we can see, so this is air sound, okay. So once air sound hit the tympanic membrane, will convert the air sound, so the air vibration to the mechanical vibration. So we can see the frequency is not changed, okay. However, in the middle ear, so the middle ear function is to amplify the vibration, okay. So we can see the mechanical vibration. So the energy of the mechanical vibration is increased, is amplified. However, the frequency is still constant, okay. Even in the inner ear, okay, in the inner ear, so the mechanical vibration is converted to the electronic action potential. So we can see the frequency is still constant. However, the mechanical vibration energy is decreased because those decreased energy is used to make the electronic nervous action potential, okay. So this is transmission of the sound. So how does this work? So let's zoom in the organ of the Coty again, okay. Since we have the outer hair cells and the inner hair cells, okay, so we can see so this is tectorial membrane, okay, tectorial membrane. Actually, so if the mechanical vibration is traveled to this region through the endolymph, okay. So the first is will cause the tectorial membrane to vibrate, okay, to vibrate, and that so this membrane will vibrate the hair, okay, vibrate here. So once the hair is vibrated, so the hair actually has the So the here actually has the specific calcium and potassium channel. Okay, so this channel will be stimulated to open to get more calcium and potassium ion travel into the hair cells. Okay, travel into the hair cells. So the hair cells is depolarized. Depolarized. If the cell is depolarized, it will release the neurotransmitters to the synapse between the hair cells and the nervous terminal. Okay, so this neurotransmitters has a glutamate. Okay, so glutamate can generate the nervous action potential. So the nervous action potential can travel through the nervous fibers to the ocular nerve. Okay, so this is how the hearing action potential is generated. Okay, so once the hearing action potential is generated, so the action potential will travel through the ocular nerve to the spiral ganglion. Okay, spiral ganglion, and then spiral ganglion sends the action to form the nerve, to form the vestibular cochlear nerve. Okay, and to reach to the medulla. Okay, medulla. So reach to the ocular nucleus, and then so the ocular nucleus sends the axons and cross to the contralateral side to the superior olivary nucleus, and then from here, so the axon of the nucleus will travel upwards to the midbrain, to the inferior colliculus. Okay, and also can send the axon to the contralateral part of the inferior colliculus. From inferior colliculus, so the axon will synapse with the neurons and axons to reach to the media geniculate body of the thalamus. Okay, so the thalamus actually will send the actions to synapse with primary auditory cortex or in the temporal lobe. Okay, so the auditory cortex will generate the hearing. So we will know. So we will hear the air sound outside. Okay, so this is the auditory pathway. So now let's talk about the vestibule. Okay, vestibule is responsible for the balance. Okay, responsible for balance. So how vestibule detects the balance? Actually, so the vestibule also use the hair cells. Okay, so we can see this hair cells. This hair cells also has hair. Okay, however, it's different from the hearing hair cells. Okay, so we can see these hair cells have different hair. Okay, so the longest one is called canocilium. Okay, so the shorter ones are called stereocilia. Okay, stereocilia. So the hairs touched with the jelly-like membrane is called otolithic membrane. Okay, otolithic membrane is very thick gel-like membrane. However, on the top of this jelly-like membrane, so there are a layer of a solid structure. So this is actually called otolith. Okay, otolith. Otolith. Actually, the otolith is the crystal of the calcium bicarbonate. Okay. So since this is crystal calcium bicarbonate, so this means so this auto lithiums are very heavy. Okay, are very heavy. So this is hair cells. Hair cells linked with supporting cells. Supporting cells can provide the nutrients, also can stabilize the hair cells. The hair cells also synapse with nervous fibers. Okay, nervous fibers. These nervous fibers are the vestibular nerve fibers. So they are responsible to transfer the action potential for the information of the balance. Okay. So this is macula. Okay, macula in the auricle and sacral. Okay, so they are responsible for detecting the balance. Okay. So as we can see here, okay, so if we move our hand, okay, if we move our hand, since otoliths are very heavy, okay, so for example, so if so this figure, so our hand is in a stationary position, okay. Actually, that means the auto lithium doesn't move, okay. So in this case, actually, the hair cells also generated the action potential, okay. So once our hand move to to the to the to the right lateral side, okay. Actually, so the autolytic will move to right, okay, move to right and pull the hair toward the kinocilium, okay, toward the kinocilium. So the kinocilium will be stimulated, okay. So the kinocilium will pull the stereocilia, okay. So all these hairs are stimulated, okay, are stimulated. So once all these hairs are stimulated, so the calcium channel and the potassium channel are stimulated and open, and more calcium ion and potassium ion travel into the hair cells to generate and to release the neurotransmitters to the to the synaptic cleft between the hair cells and the nervous terminal. Okay, so those neurotransmitters are the glutamate. The glutamate will once glutamate bind with the nervous terminal, so the nervous terminal will generate the action potential. So that means if we move our hand towards the kinocilium, so that will make more action potential. Okay, increase the impulse. Okay, so that means excitation. So if we return our hand to stationary position, so the autolytic will move to the stationary position, so the action potential will be decreased. However, if we move our hand to the left side, okay, so the autolithium will move to the left side, and then so it will stretch the hair band away from the kinocilium, okay. Once the kinocilium push the stereocilia, so all this here will be inhibited. Okay, so that means the calcium ion channel and potassium ion channel will be inhibited. So there is no potassium and potassium ion travel into the hair cells. Okay. So if there is no cut ion travel into the cells, so the cells, so the hair cells is hypopolarized. Okay, hypopolarized. So there is no glutamates released to the synaptic cleft. Okay, so the nervous terminal will be inhibited and release less action potential. So we can see here decrease the impulse frequency. So this is the inhibition. Okay, inhibition. So this is how we detect the balance. Okay. So that means if the action potential is increased, so we know, so we move our hand to the right. If the action potential is decreased, so our brain knows our hand turn to the left side. So this is how the vestibule to detect the balance. Okay. So now let's talk about the semi-circular canal. Okay, semi-circular canal is to detect acceleration. Okay, acceleration. Is to detect orientation. Okay, so how does this work? Okay, so we can see this because in the semi circular canal, so we have the specific structure. This is called the crista ampullaris. Is here. Okay, it's here. Okay, it's here. It's also called cupula. Okay, cupula. So the cupula. So we can see the cupula actually is structure, is a bulging structure. Okay, so the crista ampullaris is innervated by the fibers of vestibular nerve. Okay, vestibular nerve. Since in the canal, so they are the endolymph, they are the fluid. Okay, so it's filled with the fluid. So if we turn our head to the right or to the left. Okay, so if we turn our head, okay, so that will make, for example, we turn our head to left. Okay, so this is left, this is right. So if we turn our head to the left, it will since the semi circular canal is turned to the left. However, the fluid the fluid has relative movement to the right. Okay, so the fluid will hit the crista ampullaris. Okay, so once the crista ampullaris is hit by the fluid, so it will bend. It will bend by the fluid pushing. Okay, so if the crista ampullaris is bent, so it will stretch the fibers of vestibular nerve and generate the action potential. Okay. So we can see, so for the left side, the crista ampullaris, so the ampullaris may be hit by this way. Or, however, for the right, so the ampullaris may be hit by this way. Okay. So, for example, for this direction, so that may cause the increased action potential. However, if we hit this way, so that may inhibit the fibers of the nerves and decrease the action potential. Okay, so we have the difference of the frequency of the action potential, and then our brain will know. So we so our hand is turning. So this different of nervous impulse will help our brain to recognize our orientation, our head orientation. Okay. So actually, so this is the pathway for the balance and orientation. For our body, actually, our human use vestibular receptors, visual receptor, and somatic receptors to maintain our balance and orientation. Okay, so the vestibular receptors actually are the receptors in the in the vestibular and the semicircular canals, okay, in the inner ear, to detect our balance and orientation. Okay, our visual receptors is our eyes. Okay, so the somatic receptors are proper receptors in our muscles, tendons, ligaments. Okay, so those receptors will detect our limbs, bodies, position and orientation. Okay, for example, if we are walking, okay, and so we don't pay attention, and then we fall, on the floor. Okay, so first of all, when we are falling, so our inner ear, so our vestibule and the circular canal will detect our orientation and balance information. Okay, so the vestibule will send this information to the cerebellum. Okay, because our cerebellum is the cortex to maintain our body position and the movement. Okay, and since we are falling, okay, our eyes will see that, so our eyes will see our body is falling. Okay, so the visual information will be transferred to the brain, to the cortex. Okay, especially to the cerebellum. Okay, cerebellum. In the same time, so the visual receptors also send information to the vestibular nucleus complex. Okay, since we are falling, so our limbs, body's position are changed. So this changed information will be detected by the proper receptors. Okay, proper receptors, and those information, those action potential will be transferred to the cerebellum and vestibular nucleus complex. Okay, so somatic receptors also send information to the reticular nucleus. So reticular nucleus function is to let all the nucleus in our brain to communicate. Okay, to communicate. So this is called the central nervous system process. Okay, so the so the so the so this is the input. Okay, input to the central nervous system, and then so the cerebellum will regulate the vestibular nucleus to send the performing action potential to the target organ. Okay, such as the oculomotor nerve or cranial nerve. Okay, to regulate our eye movement, uh, to move our eyeball. Okay, to see where we are falling. Okay, and we also send the impulse through the nerve, such as the cranial nerve. Okay, cranial nerves, spinal motor control. Okay, to control, for example, control the neck. Okay, to move our hand, Okay, and then so we can take our protective movement to prevent our falling. Okay. So this is the balance orientation pathway. Okay. So that's it. So this is this class. Okay. So I hope you guys enjoy this class. So I'll see you later. Bye.